Hello guys, my name is Arun and welcome to my channel. This series is a series of tutorials on Advanced Fortran programming. Now in this tutorial, we'll be revisiting one of the earlier methods we saw in the basic programming tutorial on Fortran programming tutorial, namely the Gauss elimination method. Now what we'll do is that we'll do this entire Gauss elimination method in a single program. Sorry, we'll do this in comparison with a Forall statement. Okay, and we'll also look at how this can be done using the do loop statement, and I'll explain you guys how these two kind of differ. Okay, the reason why I repeated this statement is because I want to indicate you guys one major thing that happens in do loop for all statements that you have to keep in mind while doing certain jobs. Okay, and now as usual, what I did is that you just have to define all the variables that you want for your entire process. I'm defining all the variables on the top here. I'm setting this to a 3 by 3 matrix. Okay, whose values are let's say whose values are you know becomes whose values are defined on the top below. Sorry. Now A is the matrix whose values will be defining is explicitly over here using this reshape command, and ident is actually identity matrix just for just for formality, but it's not exactly required. I kind of put it, but okay. Here I have two matrices AB and AIB. These two are the augmented matrix that I'll be getting by merging A and B matrix over here. Simple as that. These two are just augmented matrices. One matrix will be operated using the do loop statement, whereas other matrix will be operated using the for all statement to indicate a difference and a difference of how things can be made. Okay, simple. And then B and X are actually two-dimensional matrices with n rows and one column. I could have defined this as a one-dimensional matrix, but one-dimensional array, but I had to define like this because there was some indexing issue that came while using using a certain function and all. So that doesn't matter. It works. And then det A and T1. Det A is actually the determinant of the matrix A, and T1 is actually a temporary variable I'm going to use. And T3 is again another temporary array, but it's a one-dimensional, one-valued array. I know you could have used with just T3, but I used it. I'll explain you guys why. And then if not assigning manually, we can use this function and all to get the matrix A and get the matrix B separately in a nice way, nothing more. And we're not going to use over there. Okay, and we'll be setting the shape of A and B in these lines using the reshape command. Don't worry about the values. If we just print the matrix in a proper manner, we'll get the answers. Okay, and this function detf will return the determinant of the matrix A to this value det A. Get underscore ident will return the identity matrix. This function will return the identity matrix to the matrix ident. Get underscore AB will return the augmented matrix of this set A and B, and to the matrix AB. AIB is just a replica of AB. We'll be using separately, and using the print underscore mat2 function, and mat2 function, I'm going to print matrix A. The determinant A will be printed here because we get the value here. Okay, matrix in identity matrix will be printed here. The matrix B will be printed here. The matrix AB will be printed here. Even the other replica augmented matrix will be printed here. And this is where the entire Gauss elimination method happens. Now, for those of you guys who don't understand how this looping mechanism works, I have written a small explanation over here. Now, when you do a Gauss elimination method, what you need is that you need an augmented matrix. Okay. Now, this is the explanation. your matrix, your coefficient matrix, okay, for Gauss for if you express the okay, let me explain this a little clearly. Suppose if we have a set of simultaneous linear equations, okay, so let's say you have m equations, then you, if you want to solve it, then you need m variables in these m variables. So you need m equations each having m variables, okay, with connected to each other some kind of algebraically, such that the right hand side they all equal, some linear combination of these equal to some right hand side value. Now if you have that kind of a situation, what you'll have is that the coefficient of all these values, okay, then what you can do is that you can express that set as like this, as a linear as a combination like this, where A is a square matrix and X is a vector containing all the unknowns in the column format, and B is the right hand side value, simple. Now if you combine A and B, we get if there are m unknowns and m equations. Only if you have this kind of a scenario, you can go for this you can go for this matrix method and all. Anyway, and when you go for Gauss elimination, if you cut A becomes a m by m matrix or a square matrix, B becomes a m by 1 matrix. Okay, now when you combine A and B, you get an augment matrix of order m cross m plus 1. This this X is nothing but nothing but a cross. It's not an X. It's a little hard to differentiate. Okay, cross. Yeah, that I think this makes sense. Okay, m x is a cross, so you'll get a value like this, a matrix like this. So so if you were to write them in proper order with my I index and all, okay, the first index will denote the row and the second index will denote the column. Then if you write each and every element every element by its position in the matrix using the indices I for row and j for column, then you can write this first element becomes a11, and then a12 and a13 and so on so forth till the last value of A is a1m. But since it is an augment matrix, after this we'll have one more value called as b1, which is actually the first element in the B matrix, the first element in the B matrix. And then similarly you have a21, a22, a23 and all, okay, up to b2. This colon is just for separation, okay, and these triple dots are just to indicate that it just goes on like that. Then you have the third row, fourth row, fifth row, sixth row up till the mth row, and in the mth row it looks like this. It will be like am1, am2, am3, where m stands for the number of rows you have, and then finally your last value in the A matrix will be amm, and then your last value in B matrix is bm. Okay, now what does Gauss elimination method says is that it goes like this. Let's the elimination method goes in rather sets. Okay, in the first set, what you do is that you do a linear operation on the second row using the first row in the first set. Okay, in the first set, what you do is that you do a linear operation on row 2, row 3, row 4, row 5 up till all the m rows from second row till the bottom row, using row 1 as a constant multiplier as a linear combination or something of that sort. I mean, use a linear combination with I think it's not multiplier, with linear combination from row 2 used. Okay, ignore the grammar here. With linear combination as r row 1. Okay, let me name this as I equals 1. Okay, simple enough. Then what you do in the second row, let me assign j for the rows. Okay, since we are operating on second row, let j be 2. Then what happened to the first element is that First element is that if I were to do a Gauss elimination method and reduce this to an echelon form, the first set, what I'll do is that I'll just have to subtract A21 with the product of A11 times A21 and divided by A11. This way I'll reduce A21 to 0, and then I have to do the same. Since I have to do the same linear combination to all the values in the same row, what I do using the corresponding element positions in column row 1, okay, A22 becomes A22 minus A12 instead of A11 here. It's A12 times A21 divided by A11, like that, and this is A23 equals A23 minus A13 multiplied by A21 divided by A11. Now if you guys notice here, we are operating on the second row, first column, so let me keep k for column, so I have k equals 1, and then here second row, second column, so k equals 2, okay, third column, so k equals 3, so on and so forth till I get the last column, which is k equals m, and finally the k plus 1th column, which will actually the B matrix, where we'll be operating the B matrix. Here B2 will, if you follow the same convention over on the top, B2 will be actually equal to B2 minus B1, because B1 is the element that is located in the first row, corresponding to the same column index, to the same column index as that of B1. So it's B1, B2, so it's B2, okay, so B1 times A21 divided by A11, and so on. Now with this set A2 is the row 2 is reduced. Now if we repeat this set with A3, we'll have our equations will slightly modify, okay, and then the multiplication factor becomes A31 divided by A11. Alright, like that, and this is continued till the last row where j equals m. Okay, once this is done, this entire process is repeated with the second row, in the second set. In the second set, what happens is that we, instead of start in the second set, we use with linear combination from row 2 used. Okay, in the second set, what we do is that we start the job from j equals 3 or else row 3, because your first row is already done. First row we don't modify the first row at all. Second row is reduced, okay, and then now using the second row as a reference or a linear combination input, we'll have to modify row 3, row 4, row 5 and all the rows subsequent to it using that way. So that way, and when that is done, the k should be varying from 2 to m plus 1, because the element A21 A31 would have been 0 during this kind of an elimination process. If you guys notice, because of this recurring pattern over here, all the elements in the first column except A11 will be 0. It will be 0 because of this elimination. And in this second set, we have to start the k in the elimination from k equals 2 or the second column all the way till m plus 1th column. Okay, in the fourth set, like in the same set but in the fourth row, it should go from k equals 2 to m plus 1, like that, and so on. Now with this being done, the entire process has to be repeated to complete second set. And then in third set, okay, it starts from I equals 3 and j starts from 4 to m plus 1 and k starts from 3 to m plus 1 something, so like that, sorry. Okay, like that and so forth, like that. If you guys notice, there will be like there will be like several sets of this form. Okay, now if you guys notice a pattern from this, and if you use I, J and K kind of meticulously and properly, what you will get is that you will get a pattern similar to this pattern over here. You will get this pattern over here. Okay, this is what we'll get. Now if we compare the kind of if you just look at the indices and everything nicely, okay, for any condition for these your I for your case will be varying from uh, 2 sorry 1 1 to m minus 1, and your j will be varying. Okay, if you guys notice in this process, j starts one value more than I in any place. Okay, so j starts from I plus 1 till m okay, and your k will start from your I value, because if you notice in this equation, your k starts with the same value as that of I and goes till m plus 1. So these are the three these are the ranges of k, I, j, k, and the same ranges of I, j, k are used. Instead of m, I'm using n over here, but anyway, it's exactly the same. Okay, and one more thing is that and this process, if you guys notice, it will be aib j comma k equals aib j comma k minus aib I comma j, sorry, it's I comma k star, okay, star aib. Now what will this be? J comma I, okay, divided by your aib I comma I, and you end them here. To end all the loops, you just end them here. So this is the pattern you get if you guys look at the IJK notions properly. But there is one point you have to keep in mind when you do this Gauss elimination. If you guys look at this equation over here, we're using A21, and we're modifying A21 over here, and because we're using the same A21 value, we're copying the A21 value and modifying it to give a new updated value of A21. But in this next equation, when you use A21, okay, instead of the previous value, only the old value remains. So what you have to do, you have to assign this previous value to a loop which to a value and use that within the entire of this k loop. So what I did is that I just saved this aib j comma I, which that part is actually corresponding to a comma j comma I, and I used that. Okay, and I will use that value over here, so that during the repetition process, okay, the value j comma I is actually used till the end of the program, kind of till the end of this loop properly. That's the reason. So this is kind of the extremely optimized version of the Gauss elimination method. Okay, now if you want to do this kind of a process, okay, in for loop, what people might have initially think that, I'll do the same job over here, and since we saw that the matrix does not get modified until otherwise the entire loop is done like this. Okay, let me comment this out. This will work, but let me comment this out for a while. Okay, let me comment this out for a while. Okay, now instead of writing 3 loops like this, let me write something of this sort. Okay, let me write something of this sort and proceed with it. Now people might think that since the memory retention is not an issue over here, sorry, since the memory issue is not a problem over in do loop, we can write this entire stuff in a single compressed format like this. Agreed? But there's a problem over there's a problem over here. If I were to compile this, what happens is that you'll get a warning. First warning, it says that the Forall with index I is not used on the right hand side statement. So it's indicating that there will be multiple assignments to j comma k that can happen in the entire process. Well, it's just a warning, but it's okay. Just a warning. It's not a error, at least to work at. And then work at. And then it's saying an error that your Forall index I may not appear on the triplet specification. What it's saying is that if you're using a variable in the Forall statement like I, okay, you cannot use this in the same Forall again. Okay, and similarly, because of the same thing, you cannot use I over here. Now, how do we now? Because of that, this three level nested code is not available for us. So this is turning out to be an error. Now, to solve this, what happens is that what can we do is that write them in nested format. The same thing, the nested format, okay, without having this temporary variable, we'll write the same thing in the nested format, okay. Nested format. Okay, now if we were to run this, if we were to compile this, it just shows a warning that we haven't used I on the right hand side assignment, and it's saying that your matrix might have multiple assignment issues and all, okay. But it doesn't matter. But it actually doesn't matter, by the way. Okay. Now, if I were to give you guys a hint of what exactly is going on, okay, this is the column. This after this loop, the column gets modified accordingly. What happened to this? Yeah, the column gets modified accordingly. So I will give a step-by-step explanation of how things are. Okay, now to explain the memory saving stuff and all, let's print the matrix here, and instead of after, let me write this as during. The matrix during process. Here again I'll write during process. Okay, now this should not throw me an error or anything. Okay, you're not allowed, and yeah, you're not allowed to call either. If you guys notice, this is one more stuff. You're not allowed to call subroutines inside Forall statements like this. Okay, these are some of the things you have to keep in mind. So because of this thing, you cannot use Forall statements, you cannot use subroutines or other call statements inside a do loop in this Forall thing. Okay, because of a memory retention stuff, if you were to call a subroutine here to do the print the entire matrix at its current stage, it will not allow me. On the other hand, do loop acts more or less independently, and because of which, if I were to print this during the process, it won't cause me any issue. So if I were to run this, okay, now if I were to run this, what I did, I just written a shell script. I'm removing all the object files, mod files and executable files here. I'm compiling the module file first, the second, the Gauss, the application files next, and then getting the objects and building a executable here, and then executing it here. Now because of the nice feature in Genie, since I have the shell script here, I don't have to go to the terminal and run. I just have to press F5. Simple as that. Now it's just printing a lot of matrices on the top. It even prints the warning that happens, but it's okay. It's not a problem. It prints matrix A, the determinant of A, the identity matrix A, okay, the matrix B, the matrix AB, the matrix AIB, okay, before processing, and matrix AIB during process. If you guys notice, this is after the elimination of the this is after the Gauss elimination of the second row using the first row. Okay, and this is the Gauss elimination. This is the Gauss elimination of the third row using the first row. And then we go to the new process wherein we'll be eliminating the third row. We'll be doing the Gauss elimination of the third row using the second row. And after that, since the number of rows have been reached, number of rows has been hit, okay, the Gauss elimination stops. Otherwise it will be just going on and on and on like that. Okay, finally the matrix AIB after being processed is like this, whereas that matrix AB, which was processed by the same which we done the same job as that of the Gauss elimination, okay, using the Forall statement, is like this. You guys notice there's hardly any difference. There's hardly any difference. Simple as that. So, and your solution is like this, which is turning out to be correct. It's just turning out to be correct. I just check this and I kind of worked this out separately, and there were a lot of solutions on the internet. I checked them out and it worked out to be fine. Okay, this is how a Gauss elimination. This is how a Gauss elimination application works, and this is how you have to use for all statements and all. These are one of the places wherein if you were to conserve your matrix, you have to save your matrix, keep it intact from a previous value to a new updated value and all. For all statement is extremely useful, and you can, and that's one thing. And if you were to use a nested for all statement like this, you cannot use the iterating variable that are already available here in the same line for other iterators. Okay, and you cannot call subroutines or certain print functions within the for all statement and all. Okay, so these are things you have to keep in mind while doing this. Hope you guys learned something in this tutorial. Well, I found this tutorial a little interesting, and hopefully I guess you guys understood how this Gauss elimination method has been put. In the previous tutorial, I kind of ignored the fact to explain the Gauss elimination method, especially in the beginners tutorial, because I didn't want you guys to can get confused. Just wanted to demonstrate you guys as to how loopings were done. So, but you guys must be little advanced enough right now, so that I thought you might will understand how this goes by. This is kind of the pseudocode algorithm. This is kind of the algorithm that works by paper. I actually wrote this in a piece of paper, and then I kind of worked it out the stuff. I just replicated there in the text so that I can explain you guys as to what happens. This is how you get a algorithm or a pseudocode ready. Once you get something like this ready, transferring it to the code and getting the code is just a matter of time. Simple as that. Okay, thank you guys for watching, and see you guys next tutorial, and I hope you guys learned something new today. And this is how you have to use a for loop and all. Bye.